morning everyone. Today we are going to discuss about the topic that is cumulative distribution function and probability density function. I am Dr. Abhishek Joshi. I will be continuing with this topic today. In our earlier lecture we have already discussed about the continuous functions or continuous random variables. So the cumulative distribution function. So what is the cumulative distribution function? We denote the cumulative distribution function by fx. Here you can see. So this one, the cumulative distribution function, we have f of x. This is a representation of the cumulative distribution function of a random variable, that is x. So x is a random variable, and we have already discussed in our previous lecture what is a random variable, which have the random values. For example, while tossing a coin is a event, and what is a random variable? Random variable may be the outcomes of the event. Outcome of the event, for example, the number of heads while tossing a coin will be a random variable. So this is a random variable. So in this lecture we are going to discuss the cumulative distribution function. So the x is a random variable, has a probability that x takes a value less than or equal to x. So this cumulative distribution function of x is equals to the probability that x is less than the x. We can show that the cumulative distribution function or the cumulative distribution f of x, or you can say the probability, has the following four properties. So what are those properties? We have the first property that f of x is greater than equals to 0. So the value will be either equals to 0 or it will be greater than equals to 0, because in our next slides we will see that it is nothing but it is the addition of the probabilities for different outcomes. So we'll prove it with the help of example in our next slides. So we have the f of x at infinity, because we know that the maximum value of the probability is 1. So while adding all the probabilities for all the outcomes for all the events, we are getting the maximum value as 1. Similarly, we can see that the cumulative distribution function for minus infinity, because minus infinity the value will be 0. So because we know that the cumulative distribution function will be either equals to 0 or it will be equals to or greater than 0. So here at minus infinity it is equals to 0. If we consider a random variable for a value x1, and we know that x1 is less than equals to x2, so we can write the cumulative distribution function, which is nothing but for cumulative distribution function for x1 is less than equals to the cumulative distribution function at x2 for the condition that x1 is less than equals to x2. So these are the four important properties of cumulative distribution function. So we have to understand these four properties, then only we can solve numerical based on the cumulative distribution function. So the first property, which is obvious, and the second and third property can be proved by the f of x at infinity and is equals to the probability that x is less than equals to infinity. And the cumulative distribution function at minus infinity, because the random variable will have the value at minus infinity which is equals to 0, because we don't have any value. So we have the probability that x is less than equals to minus infinity. So that is 1, that is 0. Obviously we don't have any value for that. Now we can prove this property. We have the fourth property that the function, that is a cumulative distribution function, we have for x2, the cumulative distribution function at a random variable x2, that is equals to the probability that x is less than equals to x2. So we can write this probability for x is less than, for example, you can consider a probability having values, discrete values at discrete values, discrete random variable. So we can have these type of values. So you can consider this as the x, and this is the probability of x. So what we have, so this means we are considering these 2 points x1 and x2. Okay. So while considering these 2 points x1 and x2 in the probability distribution, so what we can write, we are writing this as the probability that x is less than x1, this means this region, entire region, and with a union of x is less than or between x1 and x2. So if it is between x1 and x2, this means this region. So this entire region is covered by this cumulative distribution function of x2. But when we are writing for x1, it is covering the entire region, that is less than x1. Okay. So we have written this thing for x2. Similarly, because x is less than equals to x1 and x1 and x2, the x is lying between x1 and x2 are disjoint, as we have seen in this figure. So we have written this as the function for x1 and the probability for this, or you can say between x1 and x2, multiply with the cumulative distribution function for x2. So because the probability that is between x1 and x2 is a non-negative, the result follows. So what it follows? It follows this. Let's consider one example. We will solve one numerical based on this, and we will see how we can find the cumulative distribution function. So by considering one event, so what is the experiment we are considering to understand it? So we have an experiment. A trial consists of 4 successive tosses of a coin. If you define an random variable x, so what we are defining? We are defining a random variable x as the number of heads appearing in a trial. So what is x? X is a random variable for number of heads. So we will understand it how we can find. So while tossing a coin, and it is saying that we are tossing a coin for 4 times. So how many outcomes will be there? There will be 4 possible, or you can say the 4 consecutive results. And how many possible outcomes will be there for the experiment? So there is 2 raised to power 4. So we will have 16 possible outcomes, okay, for an experiment for while tossing a coin 4 times. Okay. Now let us take all the possible outcomes. I am writing it. And we have the combination okay, then we have the combination and we have okay, then we have this one and so you can see here how many heads are there. So number of heads I am counting, x is the number of heads. So number of heads So here you can see number of heads are, here are 4 number of heads, okay. Here are 3 number of heads, here again 3 number of heads, then 2 number of heads, then 3 number of heads, then 2 number of heads, then again 2 number of heads, only 1 head, okay. Here you can see 3 number of heads, here 2, 2, then 1, then 2, 1, here it is tail. So here it is 1 head and here 0 number of heads, okay. So here we have defined, we have counted the number of heads for all the possible outcomes, that is 16 possible outcomes, okay. Now we can count for x equals to 0. So you can see here for x equals to 0, for different values of x, here we can write for a random variable x, okay. So for x equals to 0, how many possible outcomes are there? Only one possible outcome, that is having x equals to 0, because it doesn't have any head. So we can write only one possible outcome is there for x equals to 0, okay, or you can say we have only one outcome. So here we are writing for number of heads equals to 0, the probability that, or you can say the random variable have the possible outcome as 1, okay. So number of heads, here you can write n, or you can number of heads, and the probability for the random variable x, here we can write the probability for random variable x will be, so how many possible outcomes are there? There are 16 possible outcomes. So the probability will be simply 1 by 16, okay. So we can write the probability as 1 by 16, okay. Now count for number of heads equals to 1. So if we have number of heads equals to 1, so how many possible outcomes are there? Here 1, 1, 1 and 1. So how many ones are there? 4 ones are there. So we have the number of heads equals to the random variable will be 4 possible outcomes. So we have 4, and the probability, so out of 16 we have only 4 outcomes which have only 1 head. So the probability will be 4 by 16. Now let's count the number of heads equals to 2. If we count the number of heads equals to 2, so we have 1, 2, 3, 4, 5 and 6. So how many 2's are there? There are 6 2's, or 6 you can say having 2 heads. So possible number of the random variable is 6. The probability is equals to 6 by 16. Similarly, we can find for number of heads equals to 3. So how many 3's are there? 1, 2, 3, 4. So there are 4 3's. This means it is equals to 4 by 16. Last, number of heads equals to 4. If number of heads equals to 4, there is only one possible outcomes, that is here, this one. So only one combination, one outcome having 4 heads, okay. So only one, so it is 1 by 16. So we have these combinations. I'll figure it out for you, 1 4 6 4, okay, in the next slide. So we have the probability of x for different values 0, we have okay. So these probabilities are as follow: 1 by 16, 4 by 16, 6 by 16, 4 by 16, and 4 number of heads, it is 1 by 16. So, we have written all the possible probabilities. Now, how to find the cumulative distribution function, which is the main objective of this numerical. So, we denote this cumulative distribution function, that is f of x, okay, with a subscript x, where x is a random variable holding the number of heads for an experiment tossing the coin 4 times. Okay. So, what will be the cumulative distribution function? Because we know that it is given by definition, we have the cumulative distribution function is equals to the probability that x is a random variable, that is equals to the random variable or the value x. So, here we can see what we can see here. For x equals to 0, what we have? So, simply it is 1 by 16. Simply we have to add up to x. If we consider 1, so then we have to add these two. So, we 1 by 16 and 4 by 16. So, 1 by 16 and 4 by 16 will be 5 by 16. Similarly, for number of heads equals to 2. So, there are 6 possible outcomes, that is probability is 6 by 16. So, for cumulative distribution function, we have to add these 3, 1 by 1, 4 and 6, that is 11. So, we have 11 by 16. Okay. Next is when number of heads equals to 3. So, possible outcomes are 4, but for cumulative distribution function, what we have to add? We have to add up to 3. Okay. Up to this we have to add. So, we have, when we add 1, 4, 6 and 4. So, we have 15 by 16. Okay. The last one, when we have the number of heads equals to 4. When we have number of heads equals to 4, this means we have the probability 1 by 16. But for cumulative distribution function, we have to consider all the possible outcomes, that is 16 by 16, that is equals to 1. So, you can understand how we have solved it. Okay. And you can also see that the maximum value at infinity, or the final value you can see here, it is equals to 1. Okay. And you know that the sum of the probability, if you add all the probability, that is 1, 4, 6, 4 and 1, it is equals to 1. So, summation of the probability is also equals to 1, and the maximum value you can see here for the cumulative distribution function is equals to 1, which is following this property which we have seen here, that for infinity, or you can say the maximum value of this function is equals to 1. Okay. For minus infinity, which we do not have any value, it is equals to 0, and you can see the least value here in this example is 1 by 16. Okay. So, you can understand how we can calculate the cumulative distribution function. Now, how to represent this cumulative distribution function, and what are the important remarks for cumulative distribution function, which we will see in our next slide. So, we can see from this slide what we have. We have the probability, which is we can see it is discrete in nature. Here we can see at probability is equals to 0, we have defined 1 by 16. When we have probability equals to 1, it is divided by 1 by 4. Then we have the probability at 2 is equals to 3 by 8, probability at 3 1 by 4, and probability at 4 we have 1 by 16. So, these are the discrete points, okay, for an experiment, that is tossing a coin 4 times, which we are discussing. Now, the cumulative distribution function which we are representing here, as you can see, for x equals to 0 and even for x up to x equals to 1, because we are considering that is x is less than equals to the value x. okay, or you can say x1, x2 or x3, whatever point you want to represent, you can represent. So here you are considering for x is less than equals to 0, what we don't have any value. For x is less than equals to 1, the complete step function is there, as you can see here. So we can see here this probability is discrete in nature for a discrete experiment, and the cumulative distribution function is a stepwise function, a step function we can see. So we have the step function and we have the probability as discrete function. Okay. For 1 to 2 duration, what is the probability? In our earlier slides we have calculated it is as 5 by 16. So it is represented by 5 by 16. For between 2 and 3, as you can see, between 2 and 3 we have 11 by 16. So we will represent it by 11 by 16. As you can see here, these are the values: 1 by 16, 5 by 16, 11 by 16, and last one, or you can say the step for x equals to 3, we have between 3 and 4 we have 15 by 16. For x equals to 4, where we have the number of heads equals to 4, again we have taken the maximum value that is equals to 1, and we have seen it here while calculating. So we are getting the maximum value as 1. So we have defined the probability as well as the cumulative distribution function, that is f of x. Okay. So now next topic is the continuous random variable. So what is the discrete random variable? Which holds the discrete values. For example, 1, 2, 3, these are the discrete values. Okay. And the discrete random variable will not have the value in between. For example, it will not have value like the 1.1, it will not have any value between 2 and 3 like 2.8. Okay. So when we don't have the intermediate values, it will be considered as the discrete random variable. Now for continuous random variable, a continuous random variable x can assume any value in certain interval. So we have all the possible values between interval, that will be the continuous random variable. So in a continuous of any range, an accountability infinite number of possible values exists. So we have infinite number of values, we have infinite number of possible values, and the probability for a continuous random variable, that is x for xi, as one of the accountability infinite values is generally 0. Okay. So what are the examples of the continuous random variable? Examples are the weight of the person. So weight of the person can be, it can be a 40 kg, it may be a 40.5 kg, it may be 80.9 kg. Okay. So that's why we are considering this as a weight of a person as a continuous random variable. Then the temperature at certain location. So the temperature at certain location can be a continuous random variable. Why we are calling it as continuous random variable? Because we have the temperature can be 16.1, the temperature can be 30.5, or the temperature can be 39.9. okay, it depends. So it can have any value. So at what resolution you are taking the value, it depends on you, but it will have all the possible number of outcomes, or all the possible values can exist in a continuous random variable. Another example we can consider as a height of individual. So height of individual can be, for example, 5.1, 5.2, or it can be 5.12. So depending on the height of a person, it will be considered as a continuous random variable. Now the another important topic, that is the probability density function. So what is the probability density function? The probability density function, we can see that is, it is we can define for that the cumulative distribution function, that is for x, for an interval or a small addition with x plus del x is equals to f of x and the probability between x and x plus del x, where del x tends to 0. So, if we consider that del x tends to 0, then we can also express, that is the cumulative distribution function f of x for x plus del x via the Taylor expansion. So, while the Taylor expansion, we can write this as, that is f of x, x plus del x is approximately equals to, using the Taylor expansion, we have f of x plus df by dx of the function f of x and del multiply by del x. So, it follows that del x tends to 0. So, what we can write here? We can write this as, we can explain this d by dx of f of x equals to the probability that x lies between x and x plus del x. So, we know that we can write this as nothing but the probability density function. So, this is the very important relation between the cumulative distribution function f of x and the probability density function. So, this is the relationship between the probability density function, or we can call it as PDF, that is the probability density function, and we have the cumulative distribution function, which is capital F of x. So, this is the relation between the cumulative distribution function, that is CDF, we can call it as CDF, and the probability density function, that is PDF. So, this is the important relation which we have to keep in mind while solving the numericals as well. So, now let us define what is the probability density function. So, what is the probability density function? The function Px is called the probability density function, that is PDF of a random variable x. It follows from equation that the probability of observing the random variable in the interval x plus del x, if the probability of x, that is multiplied by del x, is when x is equals to 0, this is the area under the PDF, that is P of x over the interval del x as shown in figure. So, how we can represent? So, this is the CDF, that is a cumulative distribution function, and we have considered earlier in our lecture, while experiment is the tossing a coin 4 times, okay, and we have described in a stepwise function, we have seen it, okay. So, here we have defined the CDF. So, we have the CDF represented by this curve, okay, in the graph, and we are considering an interval between x1, this point is x1 and this point is x2, okay. Now, between this interval, if you calculate the PDF of this function, so the PDF of the function is the area under the curve. Here you can see, or you can see here, this is the cumulative distribution function of x2 minus the cumulative distribution function of x1. But the probability density function, here we are going to differentiate it. The probability density function, here it is represented by this curve, okay, and between the interval x1 and x2, between the interval x1 and x2, if you calculate the probability density function, it will be represented by the area under the curve here, okay. So, we have the area that is equals to between the integration between the limits x1 to x2 and the probability of x dx. So, we can easily calculate, if we have the probability, we can easily calculate for a continuous random variable, we can calculate the probability density function, which result in the area under the curve, okay, that is the PDF and this is the CDF. So, we have differentiated the PDF as well as the CDF in this. So here we have written the generalized expression for this. If we want to calculate the cumulative distribution function, that is f of x. So we can, if we have the PDF, we can calculate the CDF. So simply we have to integrate it. If we integrate the density function, we will get the CDF. If we will differentiate the cumulative distribution function, we will get the PDF. Okay. So here we are written that from minus infinity to x, that is, and px u du. This is a generalized case. Now we will prove it. So we can see the probability between the interval x1 and x2, that is equals to the cumulative distribution function, that is f of x x2, and minus the cumulative distribution function of x1 and the integration minus infinity to x2, that is p of x and dx. So here we have written the final expression, that is equals to between the limit x1 and x2 p of x x dx. So the probability of observing x in an interval x1 and x2 is given by the area under the curve probability PDF x over the interval x1 and x2. So thank you. Here we are going to stop the lecture. In our next lecture we will solve numericals based on the PDF. Thank you.